Hello, folks. I'm going to be going over some more Engel and Reid Physical Chemistry problems from the book. I'm going to go over specifically some from Chapter 8, 5, 8, 13, 14, and 26. I'm only doing ones I can physically get the answers that match, so I kind of pick and choose. Problem is as follows. I just put this over here. Within what range can you restrict the values of P and T, so pressure and temperature, in the following information is known about CO2? Use the figure 8.12 from the book, 8.12, to answer the question. Temperature is increased, solid is first converted to a liquid and then subsequently to a gaseous state. So the solid melts and then boils. B, interface delineating liquid and gaseous phases is observed throughout the pressure range between 6 and 65 atmospheres. So we're getting both of them at the liquid and gas, same time at 6 and 65 atmospheres. Solid, liquid, and gas phases coexist at equilibrium. That sounds like a triple point. And only a liquid phase is observed in the pressure range from 10 to 50 atmospheres. Finally, increase in temperature from negative 80 degrees Celsius to 20 degrees Celsius converts a solid to a gas with no intermediate liquid phase. So let's go to that thing. So 812. Looking at it here. 812. So the first one asks for to go from liquid as temperature increases, solid, liquid, gas. So really, the only way we can do that would have to be below the critical point. So somewhere, the critical point right there. That's about, hard to say, maybe 90, 80 atmospheres. So between 80 atmospheres and the triple point, which is 5.11 atmospheres. So somewhere between those two spaces, as we heat, it will go solid to liquid to gas. So that's all we can limit that. So now from 6 to 65 atmospheres, as interface between liquid and gas remains. So 65 would be, so I'm guessing maybe that's 65. So in that case, we'd have to carefully follow that temperature from the triple point all the way to the critical point. Because that's where we're riding the line of it's boiling, but it's also condensing. So we'd have to very carefully follow that interface. Solid, liquid, gas coexist. Well, that only occurs at the triple point, and they've conveniently labeled that for us. Then it said liquid is observed between 10 and 50 atmospheres. We can go anywhere from negative 50, let's say, about negative 50 to where approximately the triple point, which is about 30 degrees. So we're just trying to limit ourselves into this range before the critical point. And then finally, when we increase from negative 80 to 20, a sublimation occurs. So that really limits it from standard atmosphere, maybe a little bit above standard atmosphere, up to the triple point. So only in that little range of pressure, will we achieve sublimation. But so we're just trying our best to correctly read this. And then, so, just trying to understand what exactly is going on. So 8.5 is relatively straightforward. Going back to the problems now. Looking at 8.8, let's read this problem. Oh, God. So 8.8, it has been suggested that the surface melting of ice plays a role in enabling speed skaters to achieve peak performance. Carry out the following calculation to test this hypothesis. At 1 atmosphere, ice melts at 273.15 Kelvin. The heat of fusion is 610.0 joules per mole. The density of ice is 920 kilograms per meter cubed, and the density of liquid water is 997 kilograms per meter cubed. So first, what pressure is required to lower the melting temperature by 4 degrees? Then assume the width of the skate in contact with ice has been reduced by sharpening to 19 times 10 to the negative third centimeter width, and the length of the contact area is 18 centimeters. If this and the skater has a mass of 78 kilograms balanced on one skate, what pressure is exerted on the interface of the skate and the ice? What is the melting point of ice under this pressure? And then finally, the temperature of the ice is at negative 4 degrees. Do you expect melting of ice in the ice skate interface to occur? Okay, so to start off number 8, we're trying to calculate essentially Clausius-Clapeyron, that the dP is equal to the delta H of fusion over the delta V of fusion, integral 1 over T dt, which becomes our equation that it's simply that our change in pressure is going to be equal to a constant 610 joules per mole divided by a change in volume in essentially the liters per mole. ln Tf over Ti. Now, one thing we'll need to do is to turn joules into atmosphere liters. So the first thing I'm going to do is turn 610 joules per mole into the fact that there's 101.325 joules in 1 atmosphere liter, and that converts that into something like 59.314 atmosphere liters per mole. Now, to calculate your change in volume. Change in volume, it's going to be the moles, the molar mass of water, which in 0.018 kilograms in 1 mole, divided by the density. So divided by, in this case, 997 kilograms per meter cubed. And we're the difference, delta V, so 0.018 kilograms per mole divided by 920 kilograms per meter cubed. That'll give you mole per meter cubed, which with that in mind, give you a really small number, but we can convert that, and knowing that, there is something like 10 to the third meters cubed in a liter, or essentially we're going to say there's 1,000 liters in 1 meter cubed. So, so let's just say 18 divided by 997 minus 18 divided by 920 give you something like the delta V being negative 0.01511.055. So we got 59.3114 divided by negative 0.01511.055 ln 269 and 273. We're dropping the temperature by 4 degrees. So 59.3114 divided by our negative 0.01511.055 and times our natural log of 269 over 273, we'd get something like 579.37 atmospheres. This is, remember, ATM liters per mole. This is now liters per mole. Those conveniently cancel out, leaving us just atmospheres. So that is A. Now B, we're calculating the pressure created by the skate. Pressure is a force applied over an area. A Newton being a kilogram meter per second squared. And a Pascal, which is our pressure, one of our units is a Newton per meter squared. So, to calculate the pressure, we're going to need some conversions. Force times acceleration. Okay, well, we're going to have a mass times acceleration is equal to a force. So the mass of 78 kilograms times the acceleration of 9.81 meters per second squared, giving us a Newton. And we're going to find our average, we're going to find the area of that skate in meters. So that means our 19 times 10 to the, that means that we're going to have 19 times 10 to the negative fifth meters times something like 18 times 10 to the negative second meters. So that is meters squared. All that said and done, you get a really large number in pascals. 2.2373684 pascals, something like that. But in 1 pascal, in 1 atmosphere, that is equal to 101,325 pascals. So 2.2373684 divided by 101,325 is something like, that's 220.81 atmospheres of force. So they're generating 220 atmospheres of force. The question is, part C, we're looking at how much does that drop the, so we're looking at what is the melting point of ice under this condition? So our change in pressure, so we're going back to the equation that delta P equals delta H over delta V ln TF over TI. Well, now we have a delta P in mind. We're saying 220.8 is our final. Our initial is 1 atmosphere. our pressure is 60. Well, we already established a lot of this stuff, so that's something like, we'll say that's our 59.314. That's our negative 0015110055. And now it's ln TF over 273. So we're figuring out this. So what is our first? Our pressure change is 219.8 times all of our relevant information, 1511055, divided by 59.314. Get something like negative 0.055995919 equals ln TF over 273. Inversing that log, and then multiplying by 273. Our new pressure, our new melting point is TF is now 271. Let's say 47. And so the final question, would this work if it's at 4 degrees? No. Clearly, it's not going to work. It's getting there, but it's not the only thing. It clearly cannot be the only thing. So it was a clever use of the Clausius-Clapeyron, but the main thing was watching your units. You need to make sure your units cancel out each step in order to make sure your answer's somewhat reasonable. Okay. Ready to look at number 13. Autoclaves are used to sterilize surgical tools require a temperature of 120 degrees Celsius to kill some bacteria. Water is used for this purpose. At what pressure must the autoclave operate? So we're looking at what pressure does it need to raise the temperature of boiling to 120. So again, Clausius-Clapeyron, I think, is our big friend here. Clausius-Clapeyron, just that in this case, for ln PF over PI equals negative delta H over R, 1 over TF minus 1 over TI. That okay. If normal, if we want to raise this, step 1 is we probably should calculate delta H. Delta H. So calculate delta H. You can look at the enthalpy of vaporization, the enthalpy of water minus the enthalpy of the enthalpy of steam minus the enthalpy of water would give us 285.8 would give us our enthalpy as 44 kilojoules. So we're just simply solving. We might want to adjust your enthalpy. You could maybe adjust your enthalpy at 373, but we'll use this for now. So ln, what pressure would we have to be at if the initial pressure is 1 atmosphere? 44,000 over 8.314 to change the temperature from 373 to 393. So 1 over 393 minus 1 over 373. That's a really small number. Multiply it by the 44,000 but divided by 8.314, you get positive 0.7220, we'll say 6. And that equals ln of PF, essentially. So inverse log that. Log. And you get 206, essentially. So PF would be, you would need something like 2 bars of pressure. You need something like 2 bars of pressure to achieve that. Okay. Pretty straightforward. Moving right along to 14. You have collected tissue specimen that you would like to preserve by freeze drying. To ensure the integrity of your specimen, the temperature should not exceed -5 degrees C. The vapor pressure of ice at 273.16 is 624 Pascal. What is the maximum pressure at which the freeze drying can be carried out? So similar problem. So idea here for freeze drying is sublimation. So it's just a different version of the Clausius-Clapeyron. So PF over PI, delta H sublimation over R, 1 over TF minus 1 over TI. So to calculate delta H of sublimation is the delta H of fusion, 6.010, plus the delta H of vaporization, which is our 44. So something like 50.010 kilojoules. Now, so ln, what pressure could we do this if at 624 pascals normally? -5.0010 divided by 8.314 if we do not want to exceed -5 degrees. So 268.15, 273.16. Same general process. I'm going to plug these values in. You get ln PF over 624 pascals equals -41142. And then inverse log and multiply. You're going to have PF is equal to something like 413.5 pascals. That would be the pressure we could reduce it to and still achieve that freeze drying below 5 degrees. Last problem I'm going to do, number 26. And number 26 is calculate the difference in pressure across the liquid-air interface for A, mercury, and B, a methanol droplet of radius 125 nanometers. So this requires us to, if I'm not mistaken, utilize some of our pressure differentials. We have to use the fact that the change in pressure is equal to 2 gamma over our radius. Now, gamma is our substance-dependent thing. So gamma for mercury is 0.4855 newtons per meter. And for methanol, OH, it's 0.0 0.02207 newtons per meter. So with that in mind, when we're dealing with the radius of 125 nanometers, we need to convert that into meters. So that is equal to 1.25 times 10 to the negative 7th meters. So really, we're just calculating 2 times gamma divided by 1.25 10 to the negative 7th. And that would give you a Newton per meter squared, also known as a Pascal. So multiplying the first one, just 2 times my 0.4855 divided by 1.25 e to the negative 7th. Make sure you're doing correct order of operations, and you'll be good. You get something like the pressure for mercury. Mercury is going to be 7.768 times 10 to the 6th pascals for mercury. And for, if you do the same thing again with methanol, it's just going to be instead 3.5312 times 10 to the 5th pascals. So a lot less surface tension on methanol. So I'm not going to write that out completely.